We like to think Earth is standing still, that the sun sits quietly in the center of everything, and the rest of the universe slowly drifts around it. But that picture is completely wrong. Right now, the entire solar system is racing through the Milky Way at hundreds of kilometers per second. Every planet, every satellite, every spacecraft we've ever launched, which means when something enters our solar system from interstellar space, it doesn't arrive gently. It slams into a moving target. In the last few years, at least 3 objects from other star systems have done exactly that. They passed through our neighborhood, bent by the sun's gravity, and vanished back into the dark. And almost no one noticed. At the same time, 5 human-made machines are quietly escaping the sun's grip. They aren't heading toward famous stars the way movies suggest. They're being carried along by the same galactic current as our sun itself. Once you stop thinking in Earth-centered terms and start looking at space from the galaxy's point of view, everything changes. Trajectories twist. Destinations disappear. And suddenly, the question isn't whether we've crossed into interstellar space. It's how long we've been part of it without realizing it. The biggest mistake people make when thinking about space is assuming that stillness is the default. That planets sit calmly in place, stars are fixed points, and everything else just moves around them. In reality, nothing in the universe is standing still. Most of the time, we imagine space from a human-centered view, where Earth feels like the anchor point. From there, it's easy to think of rockets as leaving the planet and heading outward into empty space. Then we learn the heliocentric view, where everything revolves around the sunday. That already feels more accurate, but it still hides something critical. Because the sun itself is not stationary, our entire solar system is tilted relative to the galaxy, moving on a vast, curved path through the Milky Way. It's not gliding gently along a flat plane either. It oscillates up and down, drifting dozens of light years above and below the galactic disk as it travels. And it's moving fast, extremely fast. The sun and everything bound to it is racing around the galaxy at roughly 250 kilometers per second. That speed is already locked in. Every planet inherits it. Every asteroid carries it. And every spacecraft we launch starts with that velocity, whether we like it or not. This means that when we send a probe into space, we're not firing it from a standstill. We're releasing it from a system that's already screaming through the galaxy. And once you realize that, the idea of a simple trajectory starts to fall apart. Because nothing is just moving away from Earth. Everything is already in motion, and that motion shapes every encounter that comes next. And that's where the story starts to get strange. Once you accept that the solar system is already racing through the galaxy, the next surprise is how misleading space paths really are. Most diagrams show spacecraft flying outward in clean, elegant arcs, as if the sun were perfectly still. From that point of view, it looks like probes are carefully aimed toward distant stars, slowly climbing away from home. But that picture only works if you ignore the motion of the galaxy itself. In reality, every spacecraft begins its journey already embedded in the sun's galactic momentum. It doesn't shed that speed when it leaves Earth. It carries it forward, silently, as part of a much larger flow. This is why interstellar trajectories can look almost wrong when viewed from a galactic frame. Instead of neat spirals or straight lines, paths stretch, twist, and shear across space. What looks like a simple curve around the sun becomes a long, slanted thread pulled through the Milky Way. And here's the counterintuitive part. Some probes don't end up moving faster than the sun at all. In fact, a few are technically moving slower relative to the galaxy. That isn't because they lost energy. It's because of direction. When a probe heads in a direction that partially cancels the sun's motion around the galaxy, its overall speed drops. When it moves with that flow, the speed increases. Everything depends on how those vectors line up in three-dimensional space. The result is that none of our interstellar probes are dramatically outrunning the sunday. They're separating from it slowly, drifting onto slightly different paths rather than racing ahead. Which leads to a surprising realization. The stars these probes will encounter aren't radically different from the stars our sun itself will pass. They're all part of the same neighborhood, moving together through the galaxy. But the probes are peeling away, and that divergence is what determines who they'll meet. And once we start tracking those encounters, the distances become more humbling than anyone expects. So far, humanity has launched only 5 machines that will truly escape the sun's grip. 5 silent travelers, each following a slightly different path into interstellar space. The first was Pioneer 10. Launched in the early 1970s, it was never designed to leave the solar system. It was meant to visit Jupiter, but a perfectly timed gravitational slingshot turned it into an escapee, sending it outward on a long, lonely trajectory. Pioneer 11 followed soon after. It used Jupiter to gain speed, then Saturn to change direction again, bending its path out of the planetary plane and into the dark beyond. Then came Voyager 1 and Voyager 2. Launched only months apart, they took advantage of a rare planetary alignment that won't happen again for generations. Jupiter, Saturn, Uranus, and Neptune lined up just enough to fling them outward like stones from a cosmic sling. They are the fastest of the five, but not by much. Even Voyager 1, the most distant human-made object, is crawling by galactic standards. It's moving fast relative to the Sun, but barely different from the Sun's own motion through the Milky Way. The last probe is New Horizons. When it launched, it briefly held the title of fastest spacecraft ever sent from Earth. But as it climbed away from the Sun and burned through its energy, it settled into a more modest interstellar pace. And here's the detail most people miss. Those speed numbers you often hear, the kilometers per second, are heliocentric. They describe how fast these probes are moving relative to the Sun, as if the galaxy itself were frozen in place. But once you add the Sun's galactic motion back in, the picture changes. Suddenly, these machines aren't blazing ahead into deep space. They're drifting alongside their parent star, slowly diverging, like leaves separating in a fast-moving river. Which raises an uncomfortable question. If they aren't racing toward distant stars, then what are they actually going to pass? And the answer is far less dramatic than science fiction promised. When people imagine interstellar probes, they picture close flybys, alien skies, nearby suns filling the frame. But that image collapses the moment you look at the numbers. Take Alpha Centauri. It's always the first star mentioned, the closest one, the obvious destination. Yet none of our probes are actually headed anywhere near it. Even the fastest spacecraft we've ever built will still miss Alpha Centauri by a wide margin. In fact, the closest any probe will come to any star in the foreseeable future is still measured in light years, not astronomical units. Voyager 2 gets the closest. In about 20,000 years, it will pass roughly 2.8 light-years from the Alpha Centauri system. That's not a flyby. That's a cosmic near-miss. New Horizons and Voyager 2 will eventually pass red dwarf stars as well. One comes within about 1.8 light-years. Another within 1.7. Those distances are enormous. Even at interstellar scales, they're not intimate encounters. And these estimates aren't exact. They rely on measurements that are incredibly sensitive to tiny uncertainties. Slight changes in stellar motion or galactic rotation shift the results. Half a light year here, half a light year there. But even with those uncertainties, one thing stays consistent. None of our probes are headed anywhere special. They aren't targeting stars. They aren't aiming for planets. They're simply drifting, carried by momentum, inherited at launch, and shaped by gravity long ago. Ironically, the closest and most dramatic stellar encounter in our future won't involve any spacecraft at all. It will involve the Sun itself. And that encounter has consequences far bigger than a distant probe slipping past a lonely star. While our spacecraft drift quietly through the galaxy, something far more significant is on its way toward us. A star named Gliese 710 is currently cruising through the Milky Way like any other. Nothing about it seems unusual at first glance. It's faint. It's distant. And right now, it poses no threat at all. But that won't always be true. In about 1.3 million years, Gliese 710 will pass extremely close to our solar system. Not close in human terms. Close in cosmic terms. It will sweep by at a distance of roughly 1/6 of a light-year. That's close enough for its gravity to reach into the farthest outskirts of our system. Out beyond the planets, beyond Pluto, lies a vast halo of frozen debris known as the Oort cloud. It's a graveyard of ancient comets, loosely bound to the Sun, barely hanging on. Gliese 710's flyby will disturb that cloud. Its gravity will tug on those icy bodies, knocking some of them out of place and sending them inward. Not immediately. Slowly. Over hundreds of thousands of years. From Earth's perspective, this won't look dramatic at first. No sudden explosion. No instant catastrophe. Instead, the solar system will enter a prolonged period of increased comet activity. More long-period comets drifting toward the inner planets. More unpredictable visitors from the deep freeze of interstellar space. And this is the unsettling part. That encounter will be closer than anything our probes will experience for tens of thousands of years. Closer than any star they'll pass. Closer than any destination we ever imagined for them. Which forces an uncomfortable realization. The most important interstellar encounters aren't the ones we aim for. They're the ones that come to us. And that brings us to the objects that already have. For most of human history, everything we observed in the sky belonged to the Sunday. Comets, asteroids, debris left over from planet formation. Then, that assumption quietly broke. In the last few years, astronomers identified 3 objects that did not originate here. They didn't form around our Sunday. They weren't nudged in from the outer solar system. They arrived from elsewhere. The first was Oumuamua. It appeared suddenly, moving too fast to be gravitationally bound to the Sunday. Its trajectory revealed a clear interstellar origin. It passed through the inner solar system and was gone before we fully understood what we were seeing. Then came Borisov. This one behaved more like a familiar comet, but its speed and path told the same story. It was a visitor, passing through without intention of staying. The third is 3I, Atlas, and this is the one that sparked speculation. Its trajectory didn't trace back cleanly to any nearby star system. Its motion through the galaxy was odd enough to raise eyebrows. Online discussions escalated quickly, drifting from curiosity into rumor. But when researchers rewound its path through space, the mystery sharpened instead of resolving. 3I, Atlas, didn't come from any famous star. Not Toseti. Not Vega. Not systems tied to science fiction or alien lore. Instead, its path stretched backward through the Milky Way, weaving through regions filled with countless stars, nebulae, and gravitational nudges accumulated over billions of years. The deeper scientists traced it, the less specific its origin became. Which makes sense. Objects like this aren't launched with intent. They're ejected, kicked free from their home systems by gravitational chaos, then left to wander the galaxy for eons. By the time one crosses our path, its past has been blurred beyond recovery. And yet, one detail kept the debate alive. Because if you compare how fast these interstellar visitors were moving relative to the Sun, they were faster than our probes. But that comparison hides something important. When you switch to a galactic frame of reference, their speed isn't exceptional at all. In fact, they're moving slightly slower than the Sun itself. And that single fact changes everything. Because if something were deliberately sent toward us, it wouldn't drift in like a random rock. It would stand out. And that realization sets the stage for the most controversial question of all. The moment 3I Atlas was confirmed as interstellar, speculation exploded. Social media ran with it. Forums filled with theories. And a familiar idea resurfaced. What if it wasn't natural? The argument usually starts with uncertainty. If we can't trace its origin to a specific star, then maybe it wasn't ejected at random. Maybe it was sent. But the physics don't support that story. First, there's speed. When 3I Atlas passed through our solar system, its velocity relative to the Sun looked impressive. That's what made it seem unusual. But once you factor in the Sun's own motion through the galaxy, that advantage disappears. In galactic terms, it was actually moving slightly slower than our star. That's a strange choice for anything designed with purpose. If an advanced civilization wanted to send a probe across interstellar distances, it wouldn't rely on chance encounters and inherited motion. It would add energy. A lot of it. Even with technology we can imagine today, a deliberate interstellar mission would stand out immediately. Something accelerating well beyond the local galactic flow. Something decelerating as it approached its target. We would notice that. Trajectories would bend in unnatural ways. Speeds would change over time. There would be no ambiguity. But 3I Atlas showed none of that. Its path was consistent with a natural object shaped by gravity, nudged by stars, and carried along by the same galactic current as everything else. And there's another problem with the artificial idea. A drifting object like this is inefficient. It doesn't aim. It doesn't communicate. It doesn't adjust. If intelligence were involved, we'd expect intent. Instead, what we see is randomness. That doesn't make the object boring. It makes it honest. Because these visitors tell us something deeper than any sci-fi explanation. They reveal a galaxy filled with debris, motion, and long-forgotten history, where objects wander for billions of years before briefly intersecting our path. And that realization forces us to confront something uncomfortable. The universe doesn't announce itself when it passes by. It just moves on. And so do we. When you step back and look at the full picture, one truth becomes unavoidable. Interstellar space isn't some distant frontier we're preparing to reach. It's the environment we've already been moving through this entire time. Our solar system is not a fixed island. It's a traveler, sweeping through the Milky Way with everything bound to it. The probes we launched didn't break free into something new, they simply drifted onto slightly different paths within the same galactic flow. The objects that visited us didn't arrive with intention or warning. They were passengers of the same cosmic currents, shaped by gravity, time, and chance. Their stories stretch back billions of years, erased and rewritten with every stellar encounter. That may feel less exciting than science fiction, but it's far more humbling, because it means the universe doesn't revolve around us. We pass through it quietly, briefly, and without special treatment. And yet, for a fleeting moment, our paths intersect. A comet from another star. A machine built by human hands. A future star gliding close enough to shake our distant past. Space isn't empty. It's alive with motion. And whether we notice it or not, we're already part of the traffic. The only question left is whether we'll learn to see it that way.